Neptune, the eighth and farthest planet from the Sun, has a unique position in the solar system. Discovered in 1846, it was the first planet discovered by mathematical prediction rather than direct observation. Unexpected changes in the orbit of Uranus led astronomers to suspect the existence of an unknown planet, and Neptune was found very close to the point where these predictions were made. Since then, Neptune has fascinated scientists and astronomers. Unlike the rocky inner planets, Neptune belongs to the class of gas giants, lacking a solid surface and a composition dominated by hydrogen, helium, and other gases. However, it is distinct from its larger counterparts, Jupiter and Saturn, and is often grouped with Uranus as an ice giant due to the higher proportion of ices like water, ammonia, and methane in its atmosphere. While only visited once by a spacecraft, NASA's Voyager 2 in 1989, Neptune has remained a key target of interest for astronomers. It offers unique insights into the outer solar system, the dynamics of gas giants, and the possibility of diverse and unexpected planetary behaviors far from the Sun. This distance makes Neptune an intriguing subject for study, as it raises questions about how such a remote planet can exhibit such dynamic weather patterns, massive storms, and unusual magnetic activity. Neptune's significance stretches beyond the scientific community, influencing culture, mythology, and even astrology. As we deepen our understanding of this distant giant, so will our understanding of the wider workings of the solar system and the universe itself. Neptune orbits the Sun at a surprising distance of 4.5 billion kilometers, 2.8 billion miles, taking Earth 165 years to complete the union. This great distance from the Sun is only 1/900 of the distance that Neptune gets. Despite this, Neptune's atmosphere and internal processes create some of the most extreme weather conditions in the universe. The planet's orbit around the Sun is almost circular, and it moves slowly through the signs of the zodiac, each of which lasts 13 years. This long orbital period means that Neptune has not completed a full orbit since its discovery in 1846. Its location is at the outermost end of the solar system in the pre-Kuiper region belt, a region full of icy bodies, dwarf planets, and remnants of the early solar system, and put some of them on paths that lead them into the solar system. For example, Neptune is responsible for the orbit of Pluto, a dwarf planet that travels in Neptune's orbit for part of its 248-year journey around the Sun. Neptune's orbit also means that the atmosphere is much colder, with temperatures dropping to -214 degrees Celsius, -353 degrees Fahrenheit. However, despite these freezing conditions, Neptune still displays extraordinary weather patterns, including the fastest winds recorded in the solar system, which raises questions about the internal heat sources and dynamics that drive such activity. On August 25, 1989, NASA's Voyager 2 spacecraft flew by Neptune, marking humanity's first and only close encounter with the distant planet. Voyager 2, which had already visited Jupiter, Saturn, and Uranus, provided us with unprecedented images and data, transforming our understanding of Neptune. This encounter was significant not only because it was our first glimpse of the planet, but also because it remains the only one to date. No other spacecraft has visited Neptune since, and much of what we know about the planet comes from the data gathered by Voyager 2. During its flyby, Voyager 2 passed within 4,800 kilometers, 2,983 miles, of Neptune's cloud tops, capturing detailed images of the planet's atmosphere, moons, and rings. One of the most striking discoveries was Neptune's Great Dark Spot, a massive storm system comparable in size to Jupiter's Great Red Spot. The spacecraft also captured images of Neptune's largest moon, Triton, revealing a geologically active surface with nitrogen geysers, an astonishing find in the cold, outer reaches of the solar system. Voyager 2's encounter with Neptune also provided new insights into the planet's magnetic field, which was found to be both highly tilted and offset from the planet's center. This unusual configuration suggested that Neptune's magnetic field, like that of Uranus, may be generated by complex movements within a relatively thin shell of electrically conductive fluid, rather than deep within the core, as is the case with Earth or Jupiter. The Voyager 2 mission also revealed Neptune's faint ring system, a narrow, dark ring that cannot be seen from Earth. Although Voyager 2 has told Neptune a lot, there are still many unanswered questions, bringing attention to the possibility of a possible visit to the mysterious planet. Neptune's atmosphere is composed mostly of hydrogen, about 80%, helium, about 19%, and small amounts of methane and other hydrocarbons. The methane in Neptune's atmosphere gives the planet its wonderful blue color. Methane absorbs red light from the sun and reflects blue light back into space, giving Neptune its color. It has a stronger blue color than Uranus and has a similar atmospheric composition, which scientists believe may be another unknown component to Neptune's blue appearance. Below the upper atmosphere, it becomes more difficult to form, and clouds of methane and hydrogen sulfide are released into the atmosphere. Neptune's atmosphere is divided into several layers, the upper layer consisting of frozen methane and ammonia clouds. Beneath these clouds are deeper layers of hydrogen, helium, and methane gas. As it moves toward the planet, the temperature and pressure increase, creating conditions that condense hydrogen molecules into water. Neptune's atmosphere is very dynamic, with strong winds, large storms, and large clouds moving across the planet's surface. This has led scientists to hypothesize that Neptune has an internal heat source, possibly due to the slow contraction of the planet's core that could fuel its climate. The presence of methane and other hydrocarbons in Neptune's atmosphere raises questions about the chemistry of the planet's clouds and the complex carbon dynamics of the solar system. Neptune is home to some of the most extreme and violent weather in the solar system. The planet's atmosphere is constantly moving, with strong winds reaching speeds of 2,100 kilometers per hour, 1,300 miles per hour, the fastest in the solar system. These supersonic winds are thought to be caused by a combination of the planet's internal heat and its rapid rotation, completing a complete revolution every 16 hours. Although Earth receives only a fraction of the sunlight compared to other planets, Neptune's atmosphere is very dynamic, with large storm systems and clouds swirling around the planet. One of the most famous features of Neptune's atmosphere is the Great Dark Spot, a large storm system similar in size and shape to Jupiter's Great Red Spot. The Great Dark Spot, discovered during Voyager 2's 1989 flyby, is a high-pressure system with winds reaching 2,400 kilometers per hour, 1,500 miles per hour. Unlike Jupiter's Great Red Spot, which lasts for centuries, Neptune's Great Dark Spot is shorter. When the Hubble Space Telescope discovered Neptune in the 1990s, the Great Dark Spot disappeared, but new storm systems appeared elsewhere in the universe. Neptune's atmosphere also contains bright white clouds of methane ice that originate in the planet's upper atmosphere. These clouds are thought to be similar to cirrus clouds on Earth and can be seen moving around the globe. Despite its coldness, Neptune's atmosphere is stronger than that of Uranus, suggesting that the planet's internal heat plays an important role in controlling climate systems. Neptune's magnetic field is complex and variable, 47 degrees from the planet's axis of rotation, about 55% from the planet's center. This highly curved magnetic field was one of Voyager 2's most surprising discoveries during its flyby of Neptune. Unlike the magnetic fields of Earth, Jupiter, or Saturn, which are generated deep within their cores, Neptune's magnetic field appears to be generated by electrical currents flowing within a relatively thin shell of conducting fluid, possibly a mixture of water, ammonia, and other ices, located between the planet's core and its outer atmosphere. This unusual configuration gives Neptune's magnetic field a much more complex and uneven structure, with magnetic poles that do not align with the planet's geographic poles. The planet's magnetic field also produces auroras, similar to the northern and southern lights on Earth, although they are much weaker and more diffuse than those seen on our planet. These auroras are caused by charged particles from the solar wind interacting with Neptune's magnetic field and are visible as faint, glowing patches near the planet's poles. However, because Neptune's magnetic field is so tilted and offset, these auroras are spread out over a much larger area than those on Earth, and they do not follow the same predictable patterns. Neptune's magnetic field interacts with the moons and rings, creating a complex interaction that is not fully understood. Although different in shape and strength, Neptune's magnetic field is an important indicator of the planet's internal structure and dynamics because the processes that drive the planet's magnetic field are different from those of the other giant planets.